Day 17, page 315, number 55. So, as we've established in class, I've drawn the picture here with all the general information about the mass of the Earth on the bottom left here, the radius of the Earth, and big G. Before I start, because I don't have a calculator, I'm going to be rounding all those numbers off. They're all real close to 6. So the mass of the Earth is 6 times 10 to the 24th kilograms. The radius of the Earth is 6 times 10 to the 9th meters. Big G is 6 times 10 to the negative 11th. Close enough. I'll give you the idea. If you want more exact answers here, you can plug in the specific numbers to 2 or 3 sig figs. But up in the upper right-hand corner here, they're calling it potential energy sub G. I'm calling it by the more generic term that's more common, U sub G. Same thing. I'm going to show you once again how this negative enters in, because it's important mostly to figure out the changes getting the energy, potential energy increasing as you separate the two objects. Alright, so I'm going to try to squeeze this in down here. U sub G, the potential energy of this system when you have the 1 kilogram mass sitting right on the surface of the Earth, that's 1 Earth radii, is negative G, rounding it off, well, we'll round it off to 6 times 10 to the negative 11th. And the units are still as they are down there on the left. That's big G, rounded off to 6. Mass of the Earth, 6 times 10 to the 24th kilograms, standard. Times our mass sitting there is 1 kilogram, that's nice. Divided by the radius of the Earth, which is basically 6 times 10 to the 9th meters. All of that is standard. So, once again, I can do this without a calculator, that's why I'm doing it this way. You end up with essentially negative 6 times 10 to the 7th joules. That is the least amount of energy you can have, because this doesn't work, this formula doesn't work if you start digging holes into the Earth. The closest you can be to the Earth is the surface of the Earth. So that's the energy you start with. Well, I'm going to call that U sub G 1 Earth radii. Now, if you look at the equation, we can take a lot of shortcuts. The equation at the top, which I'll circle in blue, using our basic mathematical principles, as you double the radius, in other words, if you go to 2r, like in my diagram, if you double r, the energy should go to half. Not a quarter like it is in an inverse square law. But bottom line, I don't need to calculate everything again. I know that U sub G2 is going to be negative 3 times 10 to the 7th joules. I just wanted you to see the pattern here. You know, I know I'm breaking some rules of sig figs, but we're getting the idea. U sub G3, in other words, if you triple the distance relative to the first computation, the negative 6, you're going to have 1/3 the original energy. Well, in absolute value terms, the actual energy is going up because, let me explain that. This will be negative 2 if you plug all the numbers in. So, yeah, absolute value, the number is going down, but the actual energy is going up, because the more you separate, the more energy you have. In other words, if I go from negative 6 joules of energy to negative 2, I've gained 4 times 10 to the 7th joules of energy. I'm gaining energy, so I get these less and less negative numbers. And our limit will be 0. So if I keep going here, U sub G4, which will be 1/4 of the 6th, which would be basically 1.5, negative 1.5, times 10 to the 7th joules, and so on and so forth. U sub G5, rounded off roughly, is negative 1 times 10 to the 7th joules, and finally U sub G10 will be 1/10 of the original, so it'll essentially be negative 0.6 times 10 to the 7th joules. It's going to get closer and closer to 0, but that's a higher and higher number. These numbers are increasing because they're getting less and less negative as they go along here. Now, they want you to graph this. I'm going to go to the next page, remembering these numbers. All right, so I've started the graph. It might look a little unconventional. On the vertical axis, I'm going to have my energy, my potential energy, U sub G, and I'm using it as 10 to the 7th joules, as you notice the label on the left there. And my horizontal axis is my distance in Earth radii, 1, 2, 3, 4, 5, up to 6, 7, 8, 9, 10, but 10 is the important one. All right, so this graph starts at 1 Earth radii. You can't have anything to the left of the 1 Earth radii on the horizontal axis. And at that distance, at 1 Earth radii, I'll plot the point here, you have an energy of negative 6 times 10 to the 7th joules of energy. At 2 Earth radii, it increased to negative 3. So that's at 2 Earth radii, that location there. At 3 Earth radii, if you went back to it, it was negative 2 joules of times 10 to the 7th. At 4, it was negative 1.5. At 5 Earth radii, it was roughly negative 1. And you see it's a curve where the asymptote is the x-axis. As I get a bigger and bigger Earth radii, my curve will approach the x-axis, but it'll never get there. My limit is 0. At 10 Earth radii, I believe my energy was negative 6, somewhere up in there. So if you connect them with a curve, this bottom left dot, you can't go any lower than that. You can't get any more to the left of that, but it will look something like this. So this energy curve for potential energy will look something like that, and it will have an asymptote as the x-axis. The greater the distance, the closer it will get to that 0 line. Now, in problem number, or later on, it says, in the problem, it says, what if you were to now fire a rocket straight up with a kinetic energy starting with 5.2 times 10 to the 7th joules of energy? So what you want to look at for this particular situation is the total mechanical energy of the rocket when it starts. The TME, total mechanical energy, is the GPE, U sub G, the potential energy, plus the kinetic energy. At the surface of the Earth, because this is going to be a conservation of energy problem, we're going to assume no losses. At the surface of the Earth, we have the negative 6 times 10 to the 7th joules. That's my potential energy. Plus, and we'll assume that's negative 6.0 just for argument's sake, plus the 5.2 positive times 10 to the 7th joules of kinetic energy. In other words, the total mechanical energy to start with in this problem is negative 0.8 times 10 to the 7th joules. We'll keep with the 10 to the 7th so we can do some consistent graphing on our scale. Total mechanical energy of negative 0.8 times 10 to the 7th joules. What's happening here is this rocket is being launched with a sudden burst of fuel burn. It's not continually firing the engines. It burns all its fuel within seconds or minutes of launch. So it's kind of coasting after it's been launched, but it's losing energy, or losing kinetic energy, transferring it to potential energy as it slows down, assuming it's going vertically straight up. It's maintaining, conserving the total energy. So if I graph that now, let's say in black, at launch, at the 1 Earth radii, and you might see a black dot appearing here, this rocket has a total mechanical energy of negative 0.8. Let me label some of this. This blue curve is U sub G, the total GPE, or gravitational potential energy, U sub G, over time. But the total mechanical energy is conserved. So something like this happens, and mine's not going to be perfect, but that black line is the TME over time. It doesn't change, assuming no frictional losses. All right. Now, interestingly enough, it'll ask you about this intersection point here. What happens is this. First, I'll give you the short answer, then the long answer. At that spot, that's when the rocket gets to its maximum height because it runs out of kinetic energy. So it comes to it's like throwing a ball straight up in the air. It stops right there, now it comes back down to Earth. And the reason why I know that is because the GPE cannot get greater than the total mechanical energy, because that blue line is going up, up, up. It's gaining potential energy if it keeps going towards that zero axis. Another way to look at this, if I label that y-axis, let me pause. So what I've done is I've sketched in the kinetic energy curve. The kinetic energy is maximum at the 1 Earth radii upon launch, and it's transferring out into potential, gravitational potential, U sub g, until about 6 Earth radii. At that point, the kinetic energy is zero, which means the rocket's not moving, can't go any further, would fall back to Earth. Now, if you want to actually figure out exactly where that spot is, or what is 6 Earth radii or 7 Earth radii, what you would do is at that spot, which I'm approximating at 6 Earth radii, the total mechanical energy at that spot is still the negative 0.8, but it's no longer any kinetic energy. That's all now wrapped up in the potential energy. So you go back to the potential energy formula, U sub E, or U sub G, and plug in the negative G mass 1 mass 2 over R, but you'd plug in the negative 0.8 for the U sub G. So you'd have negative 0.8 times 10 to the 7th equals the negative G, which you know what it is, 6.67 times 10 to the negative 11th. But we've rounded off a lot. Mass of the Earth, which is 6 times 10 to the 24th, times the mass of this object that we've been using, the 1 kilogram rocket. And what we don't know is R, at what radius the potential energy is equal to that amount. And once again, if we plugged in accurate numbers, we could get an R. I'm estimating that that R is 6 or 7 Earth radii. I could be off a little bit. One more thing to say, we'll have another problem come up on this, but if you were to launch a rocket or an object straight up with a kinetic energy of positive 6 times 10 to the 7th joules of kinetic energy, your total mechanical energy would be 0. That's the condition under which you have your break-even point as far as escaping the gravitational field of a planet. You would basically be launched upward, and you would slow down and slow down and slow down, and you would hit the 0 speed at infinity, the location of infinity. Or to give you another example, what if I were to launch a rocket with, say, positive 8 times 10 to the 7th joules of kinetic energy, which is more than the lowest amount of potential energy? Or in other words, if I add at the beginning, at that surface location, the negative 6 times 10 to the 7th, and then positive 8 times 10 to the 7th kinetic energy, you have a total mechanical energy of 2 times 10 to the 7th. Then that black line would be above the x-axis, and the object would never run out of speed. Once the potential energy got down to 0, then the rocket would maintain a constant velocity and a kinetic energy of that excess 2 times 10 to the 7th joules of kinetic energy. So in summary, the escape velocity, though, is when you set the kinetic energy equal to this minimum, the negative 6. If you set the kinetic energy equal to the negative 6 times 10 to the 7th joules of kinetic energy, and then solve for 1/2 mv squared, the velocity there is what we call the escape velocity, the minimum speed you need to escape that planet when fired at that given initial launch speed without any other fuel helping you after that.